My name is James. I'm one of the lead engineers on the ArrayFire project at AccelerEyes, and I'll be giving this kind of quick walkthrough on getting started with ArrayFire, which will show some of the basic principles, the basic syntax, and then we'll walk through some of the examples. So ArrayFire is a GPU software library. It's one of the biggest, most comprehensive GPU libraries available on the market. There's interfaces for C, C++, Fortran, and more. The main goal is to make it easy to make use of the GPU and to write in like a vectorized format, which maps well into the GPU, and to provide hundreds of performance primitives that you can build your algorithms on top of. It supports both CUDA and OpenCL, so you can run on everything from NVIDIA chips to Intel CPUs, the new Intel Xeon Phi chip, as well as ATI. So this is the outline of the talk today. It'll be about 20 minutes or so. First, and I'll get going, dive right in. So there's about 5 different things you kind of think about when you're programming. You want to choose something that's easy to program. There's good programmability. It's portable, meaning you can run it on all kinds of hardware. That you can run it on hardware in multiple generations. You want it to be performant. You want it to scale as you add more hardware. And you want there to be a vibrant community that you can bounce questions off of and pull code samples from. So we'll go through each one of these and show how ArrayFire builds this out. So you can think of performance and programmability as like a 2D grid or like an axis. There's on the y-axis, on the vertical axis, you can push code to be faster, or you can write slower code. So and then on the x-axis, we'll try and place things in terms of how time-consuming they are or how easy to use. So something like SSE or ABX programming those directly is very time-consuming. And on the CPU, compared to other options that will fill out this graph, it's on the slower end of things. It's much better than simply a scalar operations, but the vector width is still quite limited. Writing CUDA or OpenCL kernels, you get much more of a vector bandwidth. It's still time-consuming to write and tedious to make sure that you're not violating any parallel paradigms. Both of those are time-consuming. Now, compiler directives like OpenACC, OpenMP have started to be introduced, and those are, while easy to use, those kind of tend to have slower performance compared to libraries, which are kind of, you can treat as a black box, a closed system that's been tested and vetted, and you can, a library of reusable components you can build on top of. The ArrayFire community, just to kind of put it in perspective, we went to the different forums for like NVIDIA and AMD for their GPU section of the website, tallied up how many topics there were on their forums, and you can see how ArrayFire is apart from AMD and NVIDIA itself, ArrayFire and AccelerEyes forums are quite robust. PGI, which produces the OpenACC package, it doesn't have as big a community, but it's growing as well. Portability. Whether ArrayFire is great that you can write the same code, the same array notation, which we'll get into shortly, and you can run it on both CUDA and OpenCL hardware. With CUDA, it uses the open source LLVM compiler, and base CUDA does not provide any libraries. It's something to keep in mind. There's the kublas and kusparse and some of these others, but they're growing, but ArrayFire has a lot more libraries and functions available. for OpenCL, you can write that and you can run it on AMD and Intel and NVIDIA hardware. And also you can fall back to CPU if there's no GPU available. You can pick whatever compute device you need. Let's talk about scalability. When ArrayFire, you can write your code and you can run it on laptops and a single machine. You don't have to do any changes when you go to like your single desktop machine. When you go from a single GPU machine to a multi-GPU machine, there's all the compiling and the raw kernels are user managed and low level. With when you're using compilers and raw kernels, it's all you have to manage your own memory and resources, and it's all low level. With ArrayFire, you can just very simply switch between devices and rotate around and queue up work and move on to the next GPU and queue up work. So there's several different categories of tools. There's the compiler directives, which use these pragmas, like the open ACC directives that are introduced last year. Raw kernels can use this like launching notation. And then there's GPU libraries, which may have a simple command like reduce. MathWorks is MATLAB and provides some interfaces between CUDA and the user. And even R has started to see some support. So when you're talking about compiler directives, there's several different projects out there. When it comes to production code, OpenACC is the closest to getting that out there. And that's provided by PGI and CAPS and Cray, which are 3 companies pushing that initiative with, again, offering compilers and hardware setups. As far as research projects, two of interest are Reservoir Labs, which does R, and the Ocelot project out of Georgia Tech. These are 2 projects that kind of work with compiler directives. Now when it comes to raw kernels, when you're talking about production code, CUDA and OpenCL are the only 2 ways to write kernels. There's no real third-party compilers for kernels. When it comes to research, some projects that are brewing are the Microsoft C++ AMP render scripts and the Intel Phi intrinsics that are being developed. When it comes to libraries, of which ArrayFire is kind of one of these libraries, where in production there's a few of them that ArrayFire sits on top of. CULA, NVIDIA, and AMD all provide libraries for bits and pieces of loss and LPOC, and ArrayFire sits on top of those to pull them all together and make them interface well. When it comes to research projects, things of interest are Magma, Thrust, the NPP project from NVIDIA, which is growing in the function set very rapidly. OpenCV has a side project, which is starting to integrate the GPU, and there are others. This is to show an idea of how easy it is to use ArrayFire. On the left, you have 3 lines from ArrayFire, which do the equivalent of what you see about 26 lines on the right using Thrust. In this example, it's counting for every site, it counts the rain that was measured at that site. So it does a G4 loop, which is like a for loop, but it executes every pass in parallel, and it uses a Boolean mask over here to see if the site matches the current. For this iteration, is this measurement to be counted, and then sums all the measurements that were not masked out, stores that inside the rainfall here. In Thrust, it would look more like this. You'd define these functors, and then you'd launch them in an iterator down here, and this would be a reduction that would first transform, run this operation, and then add up all the results. So Thrust is more flexible in many ways, but the code can end up being very obtuse. And we've done various benchmarks against Thrust. And in many cases, you can think of ArrayFire as performing as good or better in all cases compared to thrust, because we make use of a lot of wherever thrust has been faster in terms of compared to our own algorithms, we've started to switch to thrust. But then for a lot of things, we write custom code that outperforms thrust and other libraries out there. For example, like the reductions here. So ArrayFire, how that kind of fits into all those categories is that it has, it's a way of adding functionality. It saves time compared to writing CUDA kernels, and it allows you to kind of do more with your code and write less of it. There's several case studies, or several dozens of case studies that are on our website where you can see where real customers have used it in production and research, achieving double-digit speedups in many cases, and in some cases there's 100x speedups. Now let's look at what the actual code looks like in ArrayFire. So to start out, we're going to look at an example which uses Monte Carlo kind of estimation to estimate the value of pi. So we'll step through this step by step. First, including this main header file for ArrayFire and opening up the namespace. Then generate 20 million random samples on a 2D grid on the unit grid, unit square. So it's a ran U for units, and 20 million of these samples in vectors, n by 1 vectors, 2 of them. And then we're going to count how many fell inside the unit circle. We're going to calculate for every one of those points. We're going to calculate the distance from origin, the square root of the distance, and see how many fell within the unit radius. And then we're going to sum all those up. And we're going to multiply by 4 because in this way, all these are positive. They're all in the upper right quadrant. We're going to multiply by 4 to kind of get an idea of how many total on the sphere, on the circle, and then divide by the number of samples we used to estimate. So that's kind of what it looks like. It's very kind of a vectorized notation. Like this is multiplying every element by every element. Under the hood, there's one array container that you saw, and under the hood there can be one of many types. There could be 32 and 64-bit floating point. It can be complex, double and single precision, or Boolean, and we also have integers, signed and unsigned. You can represent vectors, matrices, volumes, 4-dimensional, ND-dimensional data. And then you can reference subregions of arrays and matrices. You can pull out a single element, you can pull out a row, or you can use these keywords like end and span to represent an entire row, the last row, for example, here. And here's where you can pull out like a whole matrix from a volume, right? Spanning these two dimensions and taking the second slice. As I mentioned, there's several different interfaces. You can use this in C, C++, and Fortran, are the primary interfaces. Here's an example where you can integrate it with CUDA itself to malloc an array of 64 bytes, and then write single precision unit random values into that. So we'll talk about G4, which you saw briefly earlier. So you can think of it as a data parallel for loop. Whereas here's we're going to go over an example of matrix multiply, where you have a fixed B matrix you want to multiply, and you want to multiply against every slice of this A volume and store the output. So here's how it looked for 3 iterations to do the multiplication and store the result. This is what we're going to explain as the G4 notation. The loop body stays the same. And you have this G4 notation. You can have the curly braces to mark this as an option. And this will run 3 iterations. So step through that a little more. With the for loop, you have the first iteration is executed where it multiplies that vector by the matrix C and stores the result. Then you go and you do the second iteration, the third iteration. It's all serial, one after the other after the other. Completes the first one, then goes to the second one. Now with G4, it simultaneously does all three iterations. Those are all executed as if it was one big volume. So you can think of those as compiling a stacked kernel with all iterations and just doing them all on the hardware in parallel, as if they were like volumes. So another way of thinking about G4 is it kind of kicks the for loop into a higher dimension. It's like syntactic sugar to vectorize your code. You may write your loop body to be sequential, to look very like dealing with one iteration at a time. But behind the scenes, everything is compiled and tiled out to execute on all iterations in parallel. We mentioned that you can jump around to multiple GPUs. Here's an example where in a for loop, setting the device, computing random values, and then performing FFT on those random values. Kind of a nonsense computation, but shows how you can quickly jump around different devices. And keep in mind there are hundreds of functions available. You can do various reductions, like you can do vector and column row reductions. You specify along a dimension. You can do convolutions in various dimensions, 1D, 2D, 3D, FFTs in 1D, 2D, 3D, and ND. You can do interpolation, rescaling, sorting along various dimensions, and testing if something is already sorted. A lot of image processing functions to filter, rotate, reroute, dilate, resize. And then you can do a lot of linear algebra, matrix factorizations, and various scalar factors. Comparing performance here, this graph shows, as an example, matrix multiply compared against Intel's mass kernel library, the Intel MKL, as well as Eigen, Intel's performance primitives, and Armadillo. All of those are CPU libraries, and ArrayFire beats them by many multiples. Similar with reductions, ArrayFire is able to do the reductions, much of the reduction work in parallel, and so clobbers those same libraries. Convolution, here you can see the higher number, again, is better. You can see how ArrayFire reaches the higher megabytes per second throughput on the left here, and similar with 2D convolution and the gigaflops. Doing a cumulative sum and sorting. As you can see, compared to these CPU libraries, it trounces them. And also, it is as good or better than cuBLAS and the NVIDIA and CULA libraries, because in many cases we use those or improve upon them to get even further performance. So when you're thinking about ArrayFire, you're probably, or any library out there, any development option, you're thinking to yourself about whether or not to build it yourself in-house or just buy it and make use of it. So this is kind of a good graph that kind of captures what you should be thinking about and keeping in mind when you're planning things out. You can think of the two factors to consider: the cost involved and then the time involved. When you're doing development, and when you're building on your own, you're doing development, you're doing testing and QA and documentation, maintenance, importing. Oftentimes, they're so easy for the cost to balloon out. The time to do all that and maintain it, document it, it expands, and maybe it's not even your primary product really. It's only a library you want to, or a piece of functionality you want to use. ArrayFire helps eliminate all of those costs that you incur, and because we take on all the testing and QA, documentation, maintenance, importing from one generation to the next. And so we shrink each of those down. One of our customers recently made a comment about ArrayFire. He says that at AccelerEyes Investments, ArrayFire gave us a 50x speed up on our financial models, and it's really easy to use. with ArrayFire, we avoid the time sink of writing and optimizing GPU kernels by hand. This is an Australian finance firm using ArrayFire to calculate and train models and as they develop strategies. So one of the things that we work hard to do is to make sure your code is easy to maintain. You write your code once, and ArrayFire, we take responsibility for making sure every successive hardware generation is supported with ArrayFire, and your code doesn't have to change. We continually release improvements that, so if you run the same code a couple months down the road on new hardware or same hardware, just new version of ArrayFire, you'll see significant performance benefit in many cases. Best of all, it's free. For one GPU using our internet licensing server, it's fully functional, fully performance, and just requires an internet connection to connect to our license server, but it's free. There are other options, other purchase options. There's developer license, where it's one computer dedicated license, and there's also enterprise versions, which allow you to do, which offer a few more features and packaging, and also give you a lot of custom support and services to make sure that your product and your work gets done as fast as possible. You can also purchase upgrades for double precision and extensive linear algebra features, as well as multiple GPU and sparse support. Let's jump into a case study. Northrop Grumman and the Falls Church unit is working on a UAV imaging project, and they want to do ground vehicle detection as they fly over with drones and such. So here's an example image when they want to be able to pick out a lot of the cars in various parking lots and such. So they came to us with a baseline using, they already had code they've been working on for 2 years using Intel performance primitives and tuned C++ code, and it ran about 4 seconds. But they wanted it to run in near real time. And so we took that 4 seconds and pushed it into about 10x speed up to get it to 0.4 seconds. And because we rewrote the code to map to the GPU so it could run many small image patches in parallel. So we went through several different solutions. We first used ArrayFire to avoid the low-level hassle of raw CUDA. So we were able to quickly develop the solution in a matter of a week or two. And they also contracted with our services department. So we did a lot of the custom code and made sure that they delivered on time and reached their goal. And it took I think about 3 weeks, less than a month here. Well, let's jump into the demos before we wrap up. All right, we're just going to go through the Hello World example to show you how it looks. This is code that comes in the download. So if you download and you go ArrayFire 1.9 examples in the Hello World directory, and you open up the different projects. There's 2008 and 2010 versions of this studio projects. So you can see some of the syntax here. You can do random number generation, element-wise computation, FFTs, grabbing the last row, setting every other column to be 0, or negating every first 3 elements of the second column, or the middle column, 0 indexed, 0-based indexing. And so there you go. Let's switch over and let's run that now. You can also integrate or interoperate with the CPU to pull data back to the CPU and as a normal device or a normal pointer. In this case, it gets a host pointer. So I'm going to run that. I'm going to go to the, I already pre-compiled it. I'm going to go to the bin directory and run hello world. So you can see it prints out this information at the start. It, in this case, it's using a local license file and tells you which version of the toolkit is being used and linked again, so which driver is loaded up, which version of the driver. And what my computer has right now is a 2075 Tesla with about 5 gigabytes of RAM. Even detects the display device being used. So here you can see the results of each of those steps. And in the end here, it's waiting for me to hit enter. So here's where we did the sign. Here's where we did the FFT. Pulled out the last row of that FFT result. Zeroed out every other column. And negated the middle column, just the 3 elements. Anyway, are there any questions? If you have any questions, you can use the chat on the side. But that concludes the webinar. Thank you for attending. If, you can always email support@AccelerEyes with any questions, or if you want to follow up on anything, or if you want us to show any more or walk you through anything. Take care.